Well, welcome. Today's talk is going to be given by Cristian Calude. He's a professor at the University of Auckland. He's a close friend of Gregory Chaitin, who, as many of you know, came up with the concept of the omega number, which is uncomputable information. And Cristian, with a student of his, computed 64 bits of this uncomputable number. And if you want the details of why that's not a paradox, you can talk to him afterward. I had the privilege of studying with him, did my master's thesis with him on the relationship between incompleteness and uncertainty. But Cristian has spent his entire career researching and increasing our understanding of the unknowable and uncomputable. So, Cristian Calude, thank you.
Thank you very much. I'm delighted to be today at Google and to talk about one of my favorite subjects, which is Gdel's incompleteness. I'm very happy to take any questions during my presentation, so if you have anything to ask or you would like to comment in any way, just do it. Okay, so first I will start by saying what I'm not going to talk about. So I'm not going to give you a full picture of incompleteness. This is a very, very broad picture, so I will give you just a glimpse, a personal glimpse in which I have contributed a little bit. I'm not going to report a just discovered fatal flaw in the proof which invalidates the theorem. There is no such fatal flaw. And I'm not going to offer any cure for incompleteness because, again, there is no cure for incompleteness. So I apologize if I disappointed the audience. These are things that will not appear in my presentation. However, I will say something. So what I'm going to talk about is basically the following. I will very briefly say something about classical incompleteness. And I am going to ask and answer three main questions. Whether there are any really interesting examples of independent statements. These are statements which are true and unprovable in specific theories. The second one is, what is the source of incompleteness? What makes a sentence prone to be unprovable in a given formal system? And finally, how common is this phenomenon of incompleteness? Is it just a linguistic trick? Is just an accident, or it is much more than this? So these are the questions I am going to try to discuss, and most results presented in what I'm going to talk about use techniques from algorithmic information theory, which is a theory which tries to measure the amount of information in finite and infinite objects with an algorithmic flavor. So what kind of questions we may ask in order to arrive to incompleteness? So I have written here three such questions. Can we write a program to check whether a mathematical proof is correct or not? Can we write a program to generate all mathematical theorems? Can we write a program to check whether a mathematical sentence is or is not a theorem? So these are legitimate types of questions. We may hope that these questions will have a positive answer. And in order to make sense to answer such a question, we have to have a formal system, an axiomatic system in which we will be able to talk about mathematical sentences, mathematical true sentences, and mathematical provable sentences, which are the theorems. And if we look at those questions, we can easily convince ourselves that if we fix a formal theory, it is not difficult to to imagine that there is a program to check whether a sentence is or is not provable by a given mathematical proof. And this is a requirement David Hilbert put forward as an important criterion for mathematics, the possibility of having an algorithmic method, something which does not require any creativity, anything, no innovation, no Google thinking, just pure mechanical checking. Now, can we write a program to generate all mathematical theorems? Well, if the answer to the first question is yes, then the answer to the second one looks very probable to be yes as well. But what about the third one? Can we write a program to check whether a mathematical sentence is a theorem or not? Why this third question looks different from the others? Well, in the first case, I have a sentence, I have a proof, and I check the correctness. This is, something very straightforward. But here, in the third question, I have to browse all possible candidates of proofs and decide for each of them whether that specific proof is a proof for the sentence or not. If I find one, if I'm lucky, then it's perfect. I know. But what about the situation where I don't find it after 10 years or 100 years? Nothing can be inferred from this. Always there is a possibility that at the next stage, a proof will come out which will prove my sentence. So this possibility of running into an infinite search is the reason of worry. OK. Now, let's go back to 1930. And I already cited David Hilbert, who was at that stage one of the greatest, if not the greatest mathematician, pure mathematician. And he was thinking about how to make mathematics, solid in foundation. At that stage, mathematics was in the front page, not because of the results it produced, but because of the crisis of foundations. What is mathematical truth, how to prove, how to generate all mathematical theorems. And Hilbert had this important radio address in 1930, in which he basically said, there is no ignoramus. We must know, and we will know. So this credo, he challenged the whole world of mathematicians, was not only an opinion, a personal opinion, but the beginning of a program to have a universal language and a universal construction, formal construction for mathematics. But only days after, in Königsberg, when things go wrong, they go wrong very fast. So only days after this famous Hilbert address, a very young Viennese, Kurt Gdel, 25 years old, presented in the same town, in Königsberg, where the king was Hilbert, two important papers. One was the completeness of the predicate calculus and the incompleteness of Principia Mathematica. So the first one, the first paper, was not really appreciated by the audience because everybody believed it is true, and what Gdel produced was just a proof. The second one, nobody understood, with one notable exception. Von Neumann was the only one who immediately picked up the idea, and not only he understood it, but he immediately started thinking and developed, and he produced some beautiful result, which unfortunately for Neumann, Gdel already knew it. So what Gdel proved? This is the incompleteness theorem. He proves this important fact. For every effectively generated formal theory, which includes elementary arithmetic, the theory cannot be both consistent and complete. Consistent here means free of contradictions. Complete means that the theory can prove any true statement which can be formalized in the theory. And if you are not happy by talking about truth here, I can offer you a little bit more general statement here, which is a second form of incompleteness, which says that in any consistent, effectively generated formal theory, which includes elementary arithmetic, there exists and can be produced effectively a sentence of arithmetic which is neither provable nor disprovable. We don't know which between these two sentences, the sentence and its negation is true, and we don't care. But we know that both of them are unprovable. So the theory cannot basically decide between them. Now, let me give you immediately two examples, just to realize that things are not, just pure blue sky sentences. Piano arithmetic, which is a first-order theory of natural numbers, is incomplete or inconsistent, right? Either there is a contradiction, or there is a true sentences of arithmetic which piano arithmetic cannot prove. Zermelo-Frankel choice is a much more complicated mathematical formal system. It's set theory, which basically addresses the whole mathematics. This theory itself is incomplete or inconsistent. And what about, the powerful automatic theorem provers, and you have Isabelle, proof power, and so on? Are they complete and consistent? That's an interesting question. Now let me, before going to some more technical details, let me explain some things which are, again, examples, illustrations of incompleteness. As I said, arithmetic is incomplete. But in contrast, elementary geometry is complete. So there is a program you can write which decides for any sentence in geometry whether this sentence is provable or not. Incompleteness, as I said, is incurable. Each time you find an independent sentence, it means a sentence which is true and unprovable, you can add this sentence as an axiom to the formal theory. And what you get a more powerful theory, which proves everything the original theory has proved, but much more. But this new formal axiomatic system is, sick of the same disease. There are other sentences which are true and unprovable in this more powerful system. And this is true not only if I add one by one unprovable sentences, but if I add infinitely many, either in an algorithmic way or by tossing a coin, the result will be again and again a theory which is incomplete. And incompleteness is a serious challenge to Hilbert's program, which sort of thought that mathematics can be expressed in a universal way. Yes?
Is the set of all true statements well defined?
Is a set of all true statements?
Is that a meaningful concept?
It's a meaningful concept, and if you be 1 minute, I will discuss exactly. Yes, sir.
When you say a theorem is true, do you mean that adding the theorem to the system does not lead to a contradiction?
No, when I don't say a theorem is true. So when I said I am looking at the true sentences, if you wish to talk about truths in this context, some of them will be provable, some are not provable. But every theorem proved in the formal system is a true sentence. Right?
We're VCing this, so if you could ask your questions in the microphone or get it from him, we'd appreciate that. Thanks.
OK. Now, what does incompleteness not imply? It doesn't imply that 1 + 1 is 3. Now, coming to your question, it doesn't imply that there is no complete and consistent formal system for arithmetic. Because I can take as axioms, as you proposed, all the true statements about natural numbers. And there is a formal system. This system, of course, is complete because it proves every true statement. But what is the thickness of this formal system? The thickness here is that we are losing the possibility of determining whether, in a finite amount of time, whether a true sentence is or is not provable. Now, the same is, yes?
If a statement's not provable or disprovable, is it always possible to prove that it's just not provable?
In general, it is always possible to prove that a sentence is true and unprovable, but not in an algorithmic way, right? The Bible is incomplete or inconsistent, not a consequence of incompleteness theorem. Same for the constitutions. So you will see many claims of this type. Unfortunately, there are no relations. Now let me go to the more serious part of the talk. And I will address these 3 questions, whether there are interesting, natural, concrete, independent sentences. What makes a sentence incomplete, independent, unprovable? And how common is the phenomenon of incompleteness? So one of the first concrete examples of true and independent sentence was found by Gdel. And this is the consistency of the formal system itself. So Gdel has proved that if I have a formal theory which includes enough arithmetic, this theory cannot prove its own consistency. So it cannot prove that there is no contradiction in the set of theorems proved by the theory. What I mean is, in other terms, the theory will never prove P and non-P, where P is a specific sentence. But it's interesting here to observe that this theorem says the theory, say, piano arithmetic cannot prove its own consistency, but it doesn't say that a piano arithmetic consistency cannot be proved in a larger system. And indeed here, Zermelo-Frankel, which contains a mirror piano arithmetic, can prove the consistency of piano arithmetic. Of course, what Zermelo-Frankel cannot prove is Zermelo-Frankel's own consistency. Yes, sir?
When you say effectively generated, does that mean that there's an algorithm for enumerating the theorems?
Exactly. There is an algorithm. So the typical formal system consists on a number of axioms and rules of inferences, which, they generate one by one all possible proofs and implicitly all the theorems. So this mechanism can be replaced by an algorithm which generates exactly the theorems of the formal system. Now, let me give you another example. And in what I'm going to talk, Turing machines will play a formal basis of the machinery. And not only, I'm going to use a subclass of Turing machines, which are called prefix-free or self-delimiting Turing machines. And those machines have, like most programming languages, a prefix-free domain. What does it mean? If a program for this machine eventually stops, any extension of the program will not determine a computation which eventually stops. So basically, you have a mechanism, an end marker, which sort of produces delimits the program itself. This is just a technical condition, but this is essential for those who would like to look at the technicality, and it's essentially to allow us to do probability theory in this context. And one of the natural questions we may ask, we go to piano arithmetic, which, as I said, is a formal system about natural numbers in which all problems about programming, about computability can be naturally expressed. And we go to this system with a full description of a universal Turing machine. What is a universal Turing machine? Is a Turing machine which is capable of simulating any other Turing machine, like this wonderful Mac, which is capable of simulating any other computer, in particular a Windows one. So now the scenario is the following. I go to piano arithmetic, and I produce the full description of the machine. Based on this description, is piano arithmetic capable of deriving a proof that this machine is universal or not? And the results are the following. Sometimes yes, sometimes no. What does it mean, this? That the presentation of the universal machine can be sometimes open to piano arithmetic and discloses universality, and sometimes it could contain this property in a hidden, compact way that piano arithmetic cannot guess in any way, cannot certify by proof universality. And this is, this is a very, very simple example. You can't do computability without universality. Now, Mike mentioned Greg Chaitin from IBM New York, who is a very good friend of mine. We have been together to a conference in Indiana just last week. And he is the inventor of this Chaitin's omega number, which has very, very intriguing properties. But let me first mention that Turing in 1930s proved a very important result, the undecidability of the halting problem. What does it mean, this? It means that there is no Turing machine which, when presented another Turing machine and an input for that machine, decides in a finite amount of time whether the computation on that machine, on that input, eventually stops. So this means it is impossible by running a very clever procedure to know in advance whether a computation is going to stop or not. And when you fail deterministically to understand a phenomenon in mathematics, typically we look at the same phenomenon from a probabilistic point of view. And instead of asking whether it is possible to have an algorithm to solve the so-called halting problem, we ask a different question. What is the probability that given a random program to this machine, the computation eventually stops? The machine I'm talking is a universal self-delimiting Turing machine. And the answer to my question in the mathematical terms is this number of omega, which depends on the machine. It's not, this number is not like pi or e, just a unique number. It's a collection of numbers, each of them depending on the machine I'm computing the halting probability. But all these numbers share a very, very important class of properties which will be discussed in what I'm going to say something. And the first important result was proved by Chaitin, which I can present in this form. Zermelo-Fraenkel, if arithmetically sound, can determine at most finitely many bits of omega. Let me decrypt this for you. What does it mean? First of all, you remember Zermelo-Fraenkel is the most successful attempt to get a formal system in which everything in mathematics today can be expressed. So this is a formal system for the whole mathematics. What does it mean? It is sound with respect to arithmetic. It says the following. Every property of natural numbers which is proved in Zermelo-Fraenkel is true. Why is this important? It is important because you remember incompleteness applies to this system. So we cannot know whether there are, we know that there are true and unprovable statements about natural numbers, and we want this minimal sort of sanity, you know, insurance. We want to be sure that the system, when proves something about natural numbers, it proves a true property. So this number is a real number, so it can be written in binary. And the binary expansion is an infinite sequence of zeros and ones, right? And for every position in this binary sequence, I have two types of propositions. One which says that, say, the first digit is 0, and the other one says the first digit is 1. For the second part, we have one proposition which says the second digit of this number is 0, or the second digit is 1, and so on. Now, in each pair of these propositions, one is true and one is false, right? Because we have fixed the sequence of zeros and ones. And we do the following, if you imaginary experiment. We collect all the true sentences about the digits of omega, right? How many do they have? Infinitely many. How many Zermelo-Fraenkel can prove? Finitely many. So the most powerful system for mathematics is not able to reveal more than finitely many bits of this number, right? Only finitely many bits. And any proposition which is true about these bits and does not fit in this small finite set will be an instance of independent sentence, a true and unprovable sentence.
Does that mean that for a given universal machine, we can't even trivially generate an infinite number of programs that will obviously just stop immediately?
Yes.
It does mean that.
No,
because that would be an infinite
This
number.
is a true statement,
yes.
What you have said. But you see, each of these programs you mentioned will appear as a term in this infinite sequence.
Right.
Now, how these terms conspire is not at all clear at all, and this is a difference between this number, which is completely opaque, and the sequence which will give me the following information. The first, in some enumeration of the programs, the first program stops or doesn't stop, and so on. This sequence, which I guess you had in mind, has a property that it is also uncomputable because of the halting problem, but it reveals by computation infinitely many correct values, because always I can generate infinitely many correct programs which eventually stop. This is not the case here because of this, you know, conspiracy. Yes, sir.
This might be what you just answered, but is this result because you could formulate a program and the program would stop if and only if a certain statement were true? So if that statement's one of the unprovable ones, then knowing whether it would stop would be a way of proving or disproving the statement. And since we can't do that, we can't know whether that program stops.
This will be a sort of argument for the uncomputability of this number. But what I'm claiming here, and you will see it is much more. But yes, this is a way to argue that there is no algorithm which will compute the digits of the binary expansion of this number.
Okay.
But as I said, this argument is good, but not good enough to give us this theorem by Chaitin. It's good to tell us that the other number is uncomputable, where I can have infinitely many bits computed by an algorithm, but it doesn't say directly that I cannot do more than finitely for this one. And I am going to explain to you, with a little bit more work, I can exactly locate the moment when Zermelo-Frankel fails to prove anything. And this moment is the following. So this moment is, if I start looking at the digits of this number, and after the dot, I may have a number of ones, and at some moment, the first 0 appears. And then I have the rest. Zermelo-Frankel will be capable of certifying by proof only the first ones after the dot. The moment the first 0 appears, it becomes completely powerless. So this is the exact behavior, because you see the ones after the dot, they are sure. The others are unsure, and they could be forever undetermined to any algorithmic computation. And as a consequence of this result, the Solovey has proven something very interesting, that there is, and it is possible to construct effectively a universal machine which is such a bad guy that Zermelo-Frankel cannot prove not a single bit of its binary expansion. How do I get this from my theorem? Well, it's just enough to take such an omega which is smaller than 1/2. So this means after the dot, I have no 1. If I have no 1 after the dot, then everything collapses. But of course, historically, Solovey proved first his theorem, and mine came later, trying to understand exactly what happens in this construction. And this example, which is the worst possible universal machine from this point of view, furnishes an interesting class of examples of true and independent sentences. Any sentence saying the 1 billionth digit of this omega is 0, or the 1 billionth digit of omega is 1, is unprovable in Zermelo-Frankel. Why? If this condition, this sentence is false, we know that Zermelo-Frankel does not prove any false sentences about natural number. If it's true, it's not possible because of the Solovey, result. So you see, what is very important, there are two ideas which I would like to stress here. Number one, it's extremely important how you code information. All these universal machines have the same computational power, but universality is encoded in different ways. Sometimes universality is sort of open to formal systems, sometimes it's completely hidden to open system. Secondly, this kind of theorem shows that incompleteness is not something extremely complicated. You know, I have here infinitely many sentences about natural numbers. That's, you know, at the very end. It's not algebraic geometry. It's not, you know, cosmology. It's very simple number theory. And the most powerful system in mathematics is not able to say anything about this. OK. Now, let's look at another perspective of the possibility of proving things. And for this aim, I will introduce what is called the prefix complexity of a string x. And this is the minimum length of a program for the universal machine to produce a string x. So the shortest, the most compact representation for x with respect to the machine U is the, if you wish, the most compact form of U with respect to this machine. And it is possible to prove that any string has a most compact representation. And now we are asking how many statements of the forms saying the complexity of the string x is greater than m can be proved in, say, Zermelo-Frankel theory. And what Chaitin has been able to show is that if I have such a formal axiomatic system, I can effectively construct, I can program and I can construct and I can compute this number C with the properties that anything which is a sentence of this form, which is provable, cannot have M more larger than C. And in this way, you see, only finitely many strings can be certified to be complex. Everybody else is true and unprovable. And why are so many others? Because most strings have high complexity. Now, based on this theorem, Chaitin has proposed a principle which says basically the following. If you give me such a formal system, then I can contrast the complexity of the system with the complexities of the theorems proved in the system. And in systems which are interesting, the following principle will be true. The complexity of any provable sentence of the system will be smaller than the complexity of the system itself plus a constant. Now, the system being effectively generated, it is coded by a finite string. So I can construct, and I can think of the complexity of the system. I can think of the complexity of any sentence because, again, we have a string. And what this principle says, it says that in a finitely specified theory, anything which is provable cannot have a complexity higher than the complexity of the system plus a constant. Now, this is a principle which you have to, in order to justify the principle, you have to find a mathematical form of this more complex. And this system, and there are different ways to explain this. One possibility in which we were able to prove this principle was to use a complexity which we call delta. And this is the original prefix complexity minus the length of a string x. Now, I will briefly explain to you why we needed this modification from the normal standard complexity to this complexity delta. First of all, the number of strings of bounded age complexity is finite. And most interesting systems prove infinitely many theorems. So with age, you won't get anything interesting. But even more, age is a very useful, interesting complexity for strings. But when you look at strings, at sentences, it doesn't work well. And I will give you an example. If I take this very simple sentence, n equals n, what is the age complexity? Well, it goes to infinity when n grows larger and larger because you need enough coding sources to represent n. But delta complexity will be bounded because I remove from this complexity exactly those resources necessary to code n. And for this new complexity, it is possible to prove that Chaitin's principle works fine for every finitely generated formal system. Now, I am going to approach the last part with my third question, which was how popular or unpopular is incompleteness? Is incompleteness just a bunch of sentences obtained by linguistic tricks, or it's much more? And one can look at this question from various points of view, and there are at least 2 points of view which are interesting. Number one is topologically. So, you look at the geometry of those sentences and you look to see which is larger and which is not larger. And the second one is from a probabilistic point of view. You look what is probability of proving a true sentence in a formal system, and what is the probability of not proving this. So, with respect to the first question, we have been able to prove that the set of true and unprovable sentences is topologically very large. And I will give you just an analogy to understand what does it mean this. You think of all possible real numbers, and inside the real numbers you have the much smaller set of rationals, right? So in this context, the set of real numbers which are not rationals corresponds to the set of true and unprovable. This is a bigger set. In probabilistic terms, how we can look at the same question. So we have been able to prove that the probability that a true sentence is unprovable is always positive. But the probability to prove a true sentence goes to 0 and the length of the sentence grows larger and larger. So in other terms, what we can prove mathematically is very, very tiny compared to what we cannot mathematically prove. And these are 2 points of view which justify in a certain sense that this phenomenon of incompleteness represents, if you want, the norm, not the exception. And finally, let me ask a more pragmatic question. Is incompleteness bad or not? Well, of course, any kind of limit is not a pleasant result. And when this limit, attacks, if you wish, the very foundations of mathematics, is even less pleasant. I have two comments about this. The first one is that I don't find incompleteness to be such a bad situation because it forces us to be creative. So, in order to prove theorems, we cannot rely only on automatic procedures. We rely on new ideas. And the second comment which I would like to have here is that for proofs, we have Gdel's incompleteness. So there are sentences which are true and cannot be proved. But what about computation? What about computation? Do we have the same phenomenon? And the answer is no. For computation, because of the universality of the Turing machine, which was proved by Turing in mid-30s, we have completeness. So you see, there is a different status in probability. The axiomatic method is not complete. But for computation, the universal Turing machine gives you the possibility of computing everything. So in a sense, the situation in programming and in discrete computation, it is much better than the situation in probability in mathematics. So this is why you know, we love so much computer science. And I would like to add one more thing about incompleteness. As I said, incompleteness may be sort of challenged by creativity. This is not to say that completeness in computability does not require creativity. And you know very well at Google how much creativity we need to do things very well. Thank you very much for your attention. Thank you.
Thank you very much, Professor. I really appreciate you being here today. There's a piece of terminology you use which is confusing to me, and I think maybe to other people in the room too. When you have an axiomatic system like ZFC, and there's a statement A such that you can't prove A and you can't prove not A, you seem to be saying that one of those two statements nonetheless is true. And you talk about true statements that can't be proved or disproved. And if you have a statement like A, such that you can't prove A and you can't prove not A, what do you mean when you say that, well, one of them's true and one of them's not true?
Well, there are two things here. The first claim I make is that there are such sentences which cannot be proved and not disproved. And this is a sort of general statement in which I do not wish to enter in difficulties regarding what is a true statement or not. But if we do mathematics, and if we have a concrete system like Zermelo-Frankel with the continuum hypothesis, we have a clear, in mathematical logic, a clear criterion to define what is a true statement. So this goes back to Tarski, which Tarski's work very close from here at Stanford University. So in this context, when I adopt a criterion of truth, then clearly, if the theory is free of contradiction, one of the sentences P and non-P, or A and non-A, is true, the other is not. And because I'm interested only in those axiomatic systems which prove true sentences, then I have this form, which is there exists a sentence which is true and not provable in the system. So truth, once again, is something which goes from outside the system. Probability is something which goes into the system. It's like I would say, you know, at the outside level, I can see this is true, but the system itself from inside cannot see this.
So if I understand you correctly, you said that for every provable truth theorem in ZFC, there exists a proof which is not much longer than the size of a theorem plus a constant?
Yes.
So wouldn't that mean that NP is the largest possible computability class? Because if you have any statement, any computable statement, you can turn that into a theorem. If there exists a proof of that, which is not much longer than the theorem itself, then wouldn't you be able to, find it? And
I'm sorry to disappoint you. I don't think that there is a relation. At least not one which I'm aware and I can see at the moment. But if you allow me, I will make a comment regarding P. I don't think, well, P versus NP, in my humble opinion, is a very, very challenging mathematical question. But I do not see good evidence favoring that P is a class of the feasible computations. So I don't see good evidence that P is a mathematical, faithful formalization of the class of problems which can be solved by feasible algorithms.
Yeah, I was talking about NP, not P. So.
Yeah.
Hi, thanks for coming today.
Thank you.
A lot of the examples that I've seen where people point to systems and saying this sentence is a sign of the system's incompleteness or a sign of the system's inconsistencies all seem to be very pathological. They're all based on looking at the halting problem or looking at decidability. The omega constant itself deals with that quite a bit. I'm curious, if I were a mathematician who were only interested in doing things like 19th century and earlier, would I bump into incompletenesses or inconsistencies in ZFC? I'm curious if there are certain areas of math where ZFC seems to be working just fine.
Well, there are areas, as I mentioned, the simplest example is elementary geometry. Everything is complete there. And, this is much, much more general. But you pointed out to a very important, weak point in the quest of looking for independent questions. There are very few sentences proved to be independent for which a typical working mathematician will say, aha, this is something I will stop working because you have proved that it's independent. But saying this, you can turn around things and transform incompleteness from a bad situation into a good situation. So it is conceivable. For instance, let's look like Riemann hypothesis. With two other colleagues, we have proved that there is a program which has no more than 7,500 bits, which has a property that the program never stops if and only if the Riemann hypothesis is true. Yeah? Mike said about our attempt to compute bits of omega. We computed 64. 7,500 is a long way to go. But what I mean, if we were be able, you, for instance, if you tomorrow come with a proof that Riemann hypothesis is independent of Zermelo-Fraenkel, then you have an indirect proof for this. So, and there are people, Shelahi, such a mathematician, who thinks about turning incompleteness into a new tool of probability. Thanks.
Hi, it's really great having you here today.
Thank you very much.
Once again. I was very interested in your statement at the end that you have greater optimism, or I think, if I understood you right, that from a point of view, there's more power in algorithmic computation than there is in axiomatic systems.
Right. So, yes, because the computational processes form a complete set. You have completeness. You don't have completeness in mathematics, in probability. So
in what sense are computation?
Because
in what sense is this complete?
It's complete because the universal Turing machine can reproduce itself. First of all, a universal Turing machine is a finite object. It's the analog of, if you wish, Zermelo-Fraenkel system for mathematics. What is the difference between these two objects? Zermelo-Fraenkel is not capable of proving many true sentences in mathematics. The universal Turing machine is capable of reproducing any possible computational process. So this is why I think that from this point of view, there is more power in computational processes than in formal probability. And I don't know whether does this make any sense for you, but that was the contrast I tried to make.
Right. So it doesn't really hold out more hope of developing or proving more of mathematics through algorithmically than through an axiomatic system.
Well, it doesn't, but you know, there are many other things which are important in life which can be achieved through computational processes, and there is.
But aren't we sort of computer people sort of in the same boat in that it's perhaps comforting to know that anything that can be computed can be computed by some Turing machine, but if there's no effective way of finding that program, aren't we basically in the same boat as a mathematician who can't find a proof of a theorem?
Yes, yes, and there are results of this form. So there are results which say this specific computable function, this specific function can be computable by a Turing machine, but there is no way to effectively, construct such a Turing machine. Right. Yes, there are such results which sort of parallel to some extent, but you have to also acknowledge that incompleteness does not make any reference to effectiveness. In the axioms and in the rules of inference accepted by the systems we discuss here, there is no requirement that we have only constructive rules. Anything is possible. So in a sense, incompleteness, goes beyond effectivity.
Do you think there are any incomputable statements that in the future we might want to add to ZFC to make it more interesting?
What to add to?
Do you think there are any statements that can't be? I'm sorry, that can't be proven in ZFC right now that we might want to add as axioms?
Yes. Yes,
and
this is exactly. That's a very good point. This is exactly what Gdel advocated. So Gdel said that. Well, the main job of a mathematician is not really to prove theorems. This can be left to computers. But what is important is to see and distinguish between interesting mathematical sentences and trivial ones. And of course, adding new axioms in order to prove more interesting sentences is the job of a mathematician. And even this does not cure incompleteness, is a perfect legitimate way to increase our mathematical knowledge.
But what would make such a sentence interesting?
Well, the sentence by itself may not be interested. It may not be interesting, but it's interesting is what are the interesting consequences of adding this sentence to a formal system. If we get more insight, then, for instance, a typical candidate for such a new axiom is, for instance, to accept the Riemann hypothesis. And actually, even this is not explicitly many times said, many results in mathematics have the following form. If Riemann hypothesis is true, then this is true. And this is exactly like, saying, let's add the truth of the Riemann hypothesis as a new axiom and say whatever we can get.
But in order to be safe, we'd have to prove that the Riemann hypothesis could not be proven, which hasn't been done yet.
Well, if it can be proved, it is no harm. No.
But what if it's proven false? Then there's a lot of harm.
I have a quick question. You mentioned that elementary geometry is complete. Does it imply that it is inconsistent?
No, it is consistent. It is consistent, but there is an algorithm which, given an arbitrary sentence of elementary geometry, can decide whether this sentence is provable or not.
I see.
Sorry? Geometry? No, that's the point. That's the point. You can, it's a very good point, because you will say, oh, everything in geometry, we speak about pi, but we speak about 1, 2, 3, and so on. So arithmetic is in geometry. What makes geometry complete when arithmetic is not? Well, the issue here is natural numbers are not essential in elementary geometry, so we can bypass this. And the same argument we can extend by saying, is physics incomplete or not? So one wrong way to claim that physics is incomplete is to say, well, mathematics is incomplete, if you believe in what I have said here. And because physics is based on mathematics, then physics is incomplete. That's a completely flawed line of reasoning.
Why is that flawed? I didn't understand.
It's because it doesn't tell us that, it's not ruling out in any way the possibility of doing physics like we do geometry. It doesn't say that you see natural numbers cannot be avoided in doing physics. Of course, it doesn't say they can be avoided, of course. But you cannot use this type of reasoning, hand waving somehow to jump on this, stronger conclusion that physics is incomplete. It may be incomplete, but not because of this argument.
So in the example of geometry being complete, a ready available set of true but unprovable statements should be supplied by all of the arithmetic statements that you know to be true modeled in geometry. I don't know if that makes sense or not.
I'm not sure.
What's that? So you can't model in the language of geometry statements about arithmetic?
Oh, yes, that's true. So there are things about natural numbers which cannot, are not mirrored in elementary geometry. Well, I guess that there is no more questions. Once again, thank you very much.